Hello and welcome to the first video of the M3 chapter Circular Motion. No starter, we're jumping straight in. Quick overview, introduction to angular speed and horizontal circles in this video, then three-dimensional problems horizontally, then vertical circles which are a little bit different, and then objects that are not constrained to a circular path. When we're starting this, we need to consider velocity as our usual dx by dt, and arc length r theta, where theta here is in radians. So if we've got our circle, then our small section, the arc, as the particle is traveling from here to here, that's the distance it's traveling, that is r theta. So when we come to do our velocity, differentiating that, we differentiate r theta instead of x. However, when you're moving around a circle, r is fixed. That's a constant. We can take that outside of the derivative and we end up with r d theta by dt, which we can write as r theta dot. But often you won't see it written like that because this rate of change of the angle with respect to time in circular motion is given a particular name. It's called the angular speed and it's written as omega. So omega is the angular speed and the units there are radians per second. There are two key formulas to remember in this video. This is the first one here, and you need to be able to change between v and omega. Now when you see the word speed in a question, it means v. If it means angular speed, it will say angular speed. So a couple of very quick questions. Particle P is moving around a circular radius 12 at a speed of, and there we go, speed means v, 3 meters a second. Calculate its angular speed. Omega, quickly rearranging this, gives us v over r. 3 over 12 is 0.25 radians per second. Number 2. Particle P is moving with angular speed 2 radians per second around a circle of radius 4. Calculate its speed in meters per second. V equals r omega. 4 times 2 is 8 meters per second. Third one, a particle P completes 50 revolutions per minute. This is not uncommon to give it in this style. You need to change it into radians per second. That's the whole question in this case. 50 revolutions is 50 times 2 pi, 100 pi radians. And then obviously a minute is 60 seconds, so omega is 100 pi radians over 60 seconds, which is 5/3 pi radians per second. That's the first formula. The second one is to do with acceleration. Now we know acceleration is the change in velocity. So we've got change in velocity with respect to time. But in this case, our acceleration is a little bit different to usual. Usually we think of change in velocity as a change in speed. But in this case, if we've got a particle moving around a circle with constant speed v, the acceleration is due to the change in the angle. Now this can be a bit weird to get your head around. The acceleration is just due to a change in angle, or that's enough to cause acceleration, because velocity involves both magnitude and direction. And you don't need the magnitude to change, although that's usually how we've been looking at acceleration in previous chapters. But if you've got a change in angle, you're also getting a change in acceleration. So if I say we're changing theta here, at this point here, we've got a tangential speed of v. At this point, we've still got a tangential speed of v. To consider the change in this, we're going to need to split this second v, which of course is the same v, into components in the direction of the first one. So what I'm going to do is just extend this a little bit, and this angle here is also theta. So if we've got components, we've got component this way, which is v cosine theta, in the direction of the initial v, and then we've got a component this way, v sine theta, which is perpendicular to the original direction. So I've got two things I need to consider, two components. The first, v cos theta minus v, to get the change in v divided by the change in t. And the second is the same thing here, change in v divided by change in t, but for this component it's v sine theta minus 0, because initially there is no component of the velocity radially. The tangential velocity obviously is all going in the direction of the tangent. Then we need to say, okay, let's do our usual trick of making this smaller and smaller and smaller so that the angle there is not theta but d theta. And that will give us v cosine delta theta minus v over the infinitesimal time delta t, and over here v sine delta theta minus 0 over delta t. Then you need to remember your small angle approximations, and that is that sine delta theta is approximately equal to delta theta when theta is very small, which it is in this case. And cosine delta theta is approximately equal to 1 when it's very small. So this one becomes 0, and this one becomes v d theta by dt, which is theta dot, which we've already called omega. So that's the background to the final comment here, which is to say that the original direction, the tangential direction, has no acceleration if the tangential speed remains constant from this point to this point. When we look at vertical circles, we'll consider what happens if that's not the case. But for horizontal circles, we've got constant speed in most cases. However, looking in this direction, which was the sine theta component this way, perpendicular to the original direction, perpendicular to the tangent, of course, being along the radius towards the center of the circle, that has got an acceleration, and that is v omega. So the only acceleration we've got in this case is equal to v omega radially in towards the center of the circle. Now that's actually not all that useful, because generally speaking, either you'll be working with v or with omega, not with both. But we've got this formula up here again, so we can substitute out. So if we want it in terms of omega, we can substitute v as r omega, so that becomes r omega squared. Or if we want it in terms of v, we can substitute out omega and get v squared over r. So these are our two formulas for the acceleration, either r omega squared or v squared over r, depending on whether you're working with omega or v. This is the second very important formula for this video. And of course, once you've got A, you can then combine that with F equals ma to find the force involved to produce that acceleration. So here we've got a particle P of mass 2 kilograms moving on a horizontal circular path of radius 20 meters at a constant speed of 5 meters per second. The acceleration is, in this case, we're going to use v squared over r, 25 over 20, 5 over 4 meters per second squared, and then F equals ma. M is 2, a is 5 over 4, and that gives me 5 over 2, or 2.5, and it's a force, so my units are newtons. Question 2. One end of a light inextensible string of length 10 centimeters, 0.1 meters, is attached to a particle of mass 200 grams, 0.2 kilograms. Don't forget to use standard units. The other end of the string is attached to a fixed point O on a smooth horizontal table, no friction. P moves in a horizontal circle center O with constant angular speed 2 radians per second. Find the tension in the string. So it's got a circular path string here, particle here, there's tension acting inwards, looking down from above. Acceleration, in this case we're using r omega squared. The radius is 0.1, omega is 2. That gives me 0.4 for A. The only force acting is the tension. So F is equal to T, which is mass times acceleration. The mass is 0.2, 0.4 gives us 0.08 newtons for the tension. The next two examples are fairly similar to one another. If you want to skip ahead, feel free. Particle here of mass 10 grams. Again, let's change that into kilograms. Rests on a rough horizontal disk at a distance of 25 centimeters. Now, it doesn't really matter how big the disk is. What's important is where the particle is on the disk. Angular speed 1.3. The particle does not slip. Calculate the force due to the friction acting on the particle. And again, here the force is the friction. That's the only force acting that we need to worry about. So that is equal to mass times acceleration. Acceleration, I'm going to use r omega squared, 0.25. That's 1.3 squared. So the friction is equal to the mass times whatever that is. And in this case, that gives me 0.004225 newtons. Final example. Car of mass m is travelling on a flat road round a bend that is an arc of a circle with a radius 140 meters. The greatest speed at which the car can travel around the bend without slipping is 45 kilometers an hour. But let's immediately change that into meters per second. And that gives me 12.5. Find the coefficient of friction between the tires of the car and the road. So similar to the last one, the force acting here is friction. And we know if it's the maximum speed without slipping, then that is maxed out at mu r. And r we know is mg. Then over here we know that A is equal to v squared over r. 12.5 squared over 140, which is 125 over 112. And using F equals ma, we can put these together. Mu mg must equal m times that acceleration. The m's cancel out. Let's use g is equal to 9.8 in this case. Divide through by that, and we get 0.113 ... But if we've used g is 9.8, we should round that to two significant figures. And that is the coefficient of friction. Fairly simple start, just these two key formulas connecting speed and angular speed, and then the acceleration. If you can apply these formulas, you can try the questions in exercise 2A and 2B from the textbook. And maybe I'll see you in video 2.